on this computer. Okay, to all, this meeting is being recorded. This is Chemistry 2341. I'm Dr. David Irvin. I'll be your host for this. We're going to continue on with Chapter 1. We're going to finish Chapter 1 today. A few technical notes is that number one, homework will be still due today, Friday at midnight. We should have everything in either the reading assignments or the lecture to accomplish that task. And again, you do the homework on Top Hat. Okay, you don't. The links on Canvas are just to warn you when things are going to be due, and the dates that they'll be due. But everything is submitted. Both exams and homework are all submitted through Top Hat. Okay. Next week, what we'll do is we'll actually start with a few mock exams on Top Hat. These are just quick 5-minute things. Make sure that your system's working. You have all the things you need to take the exams on Top Hat. We don't have an exam for a few weeks, but I just wanted to go ahead and make sure we got all of that kind of working together. Top Hat's been pretty responsive. If you have a computer issue, I think I have the settings just right, so it doesn't require too much bandwidth, but it still gives a fairly good security to our testing facility. Okay, so we're going to finish up our slides for today, which is Chapter 1. You'll notice I have uploaded the newest sets of slides, the slides I have been using to Top Hat. There's Module 1 has been loaded and Module 2 has been loaded. And so we'll actually start Module 2 next week. There's also a third module on there called Module 1.2, which has to do with resonance structures. And I'm going to be doing a separate video lecture on that. And that's just, it's very time consuming because I have to do all the drawing and stuff. And so there'll be an additional lecture on that. But it's really to reinforce the concept of resonance structures and that we'll hit here today. Okay, I have a question in the Zoom chat. Is there any way to get Top Hat without getting the full lifetime access to the book instead of getting like a semester? It's not known whether or not OChem next semester will use this platform. So the answer to that is no. There's only one way to do it, and that's the $70 purchase for the book. Okay. And so I'm trying to make sure I get to teach this second half next semester as well so that we can do it. I know Dr. Vincentiera does use this book in her second half as well. She's teaching the second half of organic next semester, and she does use this platform as well. So I can give you information as the course goes on that which instructors do use this and don't use this. Okay, but what you'll find here is that it does go complementary to the Solomon's book and other courses. So we actually are doing about the same modules at the same time, but it would just be a difference in platform. But I know that I do and Dr. Vincentiera, Dr. V, both use this platform for teaching. Okay, does that answer your question, Zoe? Okay, so I think that does. Okay, so we're up to 32 participants, so we're a little light today, but that's Friday. So luckily, again, if you miss something, you're sick or you can't get there or your schedule changes or something, you can see these videos online at your leisure. Okay, so I believe that covers all the administration. This video should be uploaded in about 30 minutes after class. It depends on how long it takes to do that. Okay. Do we have any questions about administration or the homework before we begin with the slides for the lecture? Again, we're a small enough group you can unmute and ask your question or go ahead and put it in there. The Canvas does not support videos. It does not have enough bandwidth to do videos, so all videos are on the YouTube channel. And so the YouTube channel that you were invited to, I believe on the email, it's not on there. Wow, okay. I will, there are 2 YouTube channels that will be, one will actually just be for this course, and there's several other YouTube channels that I have for my other courses as well. But thank you. I'm gonna send you out, I'm gonna send everybody out an invite to my playlist for this class. Okay, so but Canvas does not have enough storage capacity to do the videos, so all of the videos will be on YouTube. Okay, does that answer your question? Okay, so
I have a quick question, sorry. So the homework that's due tonight is going to be the 35 question, right?
correct. The one
Okay.
on Top Hat, yes.
Okay, thank you.
You do it on Top Hat, you submit it in Top Hat, and then after it's graded, you'll be able to review it and see what you got wrong and right. And then I actually can spit out the grades from there and import them into Canvas. So, so as if you're submitting on Top Hat, your job is done. Okay, well, let me go ahead and share my screen while you guys are thinking of new questions for me. And let's see, via cable. Come on, there we go, perfect. All right, I used to do this with, actually, let me move this bar down here. I used to do this where I would do it internet and occasionally it'd glitch out on me, but it doesn't do that when I do it directly on here. So let me go ahead and move my gallery view up over here.
Oh, I actually had a quick question.
Okay.
It was actually while I was doing the homework, I just wanted to get a bit more information on how to find the orbital shape using the quantum numbers, since that kind of confused me.
Okay, so there are, in the reading assignment, it actually goes through that directly where quantum numbers associated with the number 1 are spherical, number 2, they're dumbbell shaped, 3, they have the cloverleaf shape, and then 4 get very complex. And so the 2 that you really need to pay attention to, and we're going to talk about that actually today, about how we're going from the sphericals and the dumbbell shapes to the hybrid orbitals we'll be using in this class. We'll be talking about that today.
Okay, thank you.
All right. So, and yes, you should be able to download the slides off Top Hat. There's a download button. Let me double check that right now. I'm almost positive. There is a download button. Once you get to the assigned module, it says download PowerPoint. And you should be allowed to download the original slides from there, okay? So you can download them. And the ones I have up there are the complete and full slides so that you can, you know, amend them as you go. All right, so last time we were actually talking about these structures here where we're looking at the electron domains and their geometry. So in the electron domains, there doesn't necessarily have to be an atom there, okay? It's just where like lone pairs could be or electron domains. So in the case of something like the electronic domains, it's gonna look different than the molecular geometry, because in molecular geometry, there has to be an atom present. However, the fact that you have some electron, a lone pair in one of these electronic domains changes the shape of the actual molecule too. So we need to pay attention to that. So these are the shapes of the electron domains where we can have them either linear, trigonal planar, which is as far apart as they can get, the tetrahedral, which is, again, as far apart they can get. Once you get to that 5th domain, you end up starting to blend things together and get 2 trigonal pyramidals on top of each other. And then the octahedral is 2 4-sided pyramids on top of each other. Okay, so that's the electronic geometries. So now let's look at how the molecular structure changes as we start bonding to these. So in the case of a 2 electron density areas, or that 2 electron domains, we actually end up only having a single molecular geometry associated with that. And that's where if you put an atom in each of these electron domains, or even just one atom in that electron domain, you have a linear geometry. You only have the, 2 points don't make a line, 3 points make a line. So you have to have all 3 atoms there to make a linear molecule, okay? Now, if we only have those 3 domains right there, and we have 3 things in that domain, what we end up with is a trigonal planar molecular geometry. However, if we only bond two things to that trigonal planar structure, we end up with what this is similar to what water is, which is this bent geometry. But this isn't exactly like water, because water actually has two lone pairs on it. So technically, this is not the combination for water. This would be for an ion of nitrogen, not nitrogen. This would be for an ion of like a boron difluoride with a negative charge. So we don't really, but this is not, it looks the same as the water, but it's not, okay? So when we go into those four different electron domains, that tetrahedral electron domain, if we have four things bonded to that, that means the molecular structure remains tetrahedral. And so we see that in something like methane, where we have four equal things bonded to that center atom, and they'll take up those four different domains and try to be at that 109.5 degrees. Now, if one or more of those atoms is bigger than that, than the others, that is not going to be exactly 109 degrees. That the bigger the atom, the more it's going to stretch that a little bit. Okay. So if we only have three things bonded to it and we have a lone pair, this is common in nitrogen-containing molecules because you'll have a lone pair on the nitrogen and three things bonded to it, and we'll take up this trigonal pyramidal structure. And in this trigonal pyramidal structure, the three atoms would like sit on a table forming a little platform with a three-sided pyramid here, and that lone pair is going to stick up into space. But because that lone pair is not bonded to an atom, it is not included in our molecular geometry. It's only included in our electronic geometry. So that gives us the trigonal planar. Now this last one here is what we see for water, okay? In water, we have a total of four electronic domains. Two of them are taken up by lone pairs, and two of them are taken up by hydrogen atoms. So in that case here, we also see a bent configuration, but the angle between these two atoms is trying to be 109 degrees, 109.5 degrees. It's not exactly 109 degrees because those lone pairs take a little more space, okay? So that's different than this bent geometry because these are at 120 degrees apart. So that's how we can tell the difference between being in this trigonal planar electronic with only two things bonded and the tetrahedral with the two electron domains in that bent configuration. Those two different molecular geometries have different angles between the atoms there. Okay, so what if we have more electron areas, okay? Most of the time when we're dealing with things on that group 2, the carbon, hydrogen, nitrogen, oxygen, we'll see things that have this tetrahedral electronic structure. And we'll see why that is in a little bit, okay? For some other things like sulfur and phosphorus and a lot of metals, what we'll end up with is taking that, adding another electron domain to give us that 5 electron domain. And that 5 electron domain is going to have our nice trigonal planar at 120 degrees apart. And then 90 degrees off that, we're going to have like an axis running straight through that propeller, giving us those 5 different regimes. And so if we have all 5 electronic areas bonded to atoms, we have the structure like this, which is the trigonal planar. Now, this is where molecules start getting very oddly shaped. Because if you just have a single lone pair, we can have, and 4 bonds to it, we can have this little thing called a seahorse, a sawhorse. So if you can imagine these two right here are on the ground and that can teeter-totter back and forth, okay? So if we take away one of those atoms and just leave an electronic domain, we actually end up with a T-shaped molecule here, okay? It's not gonna rearrange to give it kind of a tetrahedral or a trigonal planar, because the lone pairs are holding it in position. And then we can even get a linear if we have 3 lone pairs available to us. And that'll give us a linear structure. So it'll look like it only has 2 domains, but if we know that those lone pairs are there, we'll see that it has those 3 lone pair domains and a linear molecule. Now for the last one, this is really common within the metal systems. Where we have what we call octahedral shapes, and we can have up to 6 things bonded to the octahedral structure because we have 6 domains available to us. And so when we have all 6 covered, we call that octahedral. But when we have only 5 of those octahedral, we end up with a square plane and a bond coming out from it. So we have what we call square pyramidal. So we have a square plane of 4 atoms plus 1 bond coming out of it. And the electronic structure is on the bottom. Okay. So now if we take away 1 more bond and leave another electronic atom, we end up again with a square planar structure, because the 2 lone pairs are coming above and below that plane made by those 4 bonding atoms. And if we replace 1 more, we'll end up with another T-shaped molecule, but the T-shaped molecule is a little different because it has 3 lone pairs in it. And then again, if we substitute 1 more, we'll end up with another linear compound. However, it'll have those 4 lone pairs available to it. Okay, any questions about this? Okay. Most of the time for our group 2s, you know, carbon through fluorine, we're looking at things that have those 4 electronic domains. And therefore, we're looking for things that are tetrahedral, that are pyramidal and bent. But when we get into sulfur and phosphorus, we'll start seeing a higher number, up to 10 electrons in the system in these 5 electronic domains. Okay, so that being said, our VSEPR theory says that a carbon that has 4 equally bonded materials would give us a tetrahedral structure, okay? So because we have 4 electron domains, those electron domains are going to try to spread us apart as much as they can. And so we have to think about, okay, well, that makes a lot of sense because the electrons are going to repulse each other here. But how does that fit into our actual orbitals and orbital shapes? Okay, so because that doesn't seem to mesh really well, let's look at that a little bit. Okay, so if we were to look at the orbitals available to us in a carbon atom, and we want to bond 4 things to that carbon right here, we're going to think of this as, oh, you know, well, this is our core electrons. These don't participate in bonding. Only these 4 electrons in the second energy level will participate in bonding. And we learned that when we fill these electron orbitals, we fill it from the bottom up, and therefore we would put 2 electrons down in the s orbital, and so the s orbital is full and doesn't bond. And therefore we would only be bonding in these 2 p's right here, but we only have 2 electrons in there, which means we have to have 1 bond in 1 p, 1 bond in, let's call that the xp, 1 bond in the yp, and then 2 bonds in the zp, okay? So how can we do this, right? We're sitting there saying, okay, we're gonna have 1 bond kind of 90 degrees to the other bond, 90 degrees to that bond, and then this bond has to be out here somewhere too, okay? We don't see that structure having these 90 degrees right here that we would expect them to have if it was just bonding to these, this p orbital, and that p orbital, and then the other side of another p orbital. We do not see that structure. We would have something that was more, you know, pyramidal or trigonal or something. It would not fit this. So what's happening? What do we have to do to make this thing actually fit that tetrahedral structure we're expecting with the orbitals we have available? And so what we do is, instead of having those individual orbitals set aside like that, what we're going to do is, there's actually an extra electron here. Don't pay attention to that electron. In carbon, we have 4 electrons in our valence shell. And we have a total of 1, 2, 3, 4 orbitals, but they have different energies because 1's an s orbital and 3 of them are degenerate p's that are equal in orbital. So the only way we can have 4 equivalent electronic domains is if the energy of the s comes up and the energy of those 3 p's comes down, and they blend together to make 4 equivalent orbitals, okay? We call this hybridization of the orbitals, orbital hybridization. So instead of having this as an s and these 3 independent p's, we actually end up with 4 total orbitals of intermediate energy, and they're all equivalent. And when we do that, we had 2 electrons in this, and we had 2 electrons in this p. We end up now having 1 electron in each of those hybrid orbitals. Okay, now that we have 1 electron in each of these hybrid orbitals, and all those hybrid orbitals are the same, when we bond 4 things to carbon, it should give us that theoretical tetrahedral structure. Okay, so what that looks like is that, we're going to have our s orbital here at this lower energy, and then we have our p orbitals that are one's in the x, one's in the y, and one's in the z. So that s orbital is spherical, and those p orbitals are symmetrical dumbbells. Okay, so when we add a little bit of s to one of the p's, the dumbbell becomes unsymmetrical. One side is rounder than the other, one side is larger than the other. Okay, and so what we're going to do is we're going to take those orbitals and then try to spread them out as much as possible. So when we take one side of the orbital and make it smaller, the other side has to get bigger, and so we start to see something that looks a little bit like this orbital here. See how it's lopsided? One side has a little more s character, one side has a little less p character, and we can now start squeezing these together in the space. So if we think about it here, if we made the smaller orbital of all of these hybrid orbitals red right here, and we think about where the orbital, the backside of the orbital for this one is, it actually is going to show up right here. And so we're going to have these 3 smaller orbitals wedged in between those larger orbitals. That's the other side of that p. So that's how we're going to squeeze all 4 of them in together to make this tetrahedral shape around the central atom. Okay. So do we see that we've taken a round orbital here, blended it with a symmetrical dumbbell-shaped orbital to make an unsymmetrical dumbbell-shaped orbital, which now we can squeeze 4 of them around our central atom. Okay. Now, so we'll end up with, this is going to be what we call sp3 hybridized. 1 s orbital, 3 p orbitals for a total of 4 equivalent orbitals, which gives us this tetrahedral shape. Okay, questions on that? So because of this hybridization, we now are getting an agreement with our valence shell electron repulsion theory, saying it would be tetrahedral to have them spread out as much as possible. Okay, so what if we don't actually share all of those 3 p orbitals? Okay, what if we only share 2 of those p orbitals? This would give us a different shape, because what this would do is this would give us 3 equivalent orbitals plus 1 non-equivalent orbital that has to be somewhere else. Okay, so when we do this, we actually can form a different type of bonding. So we'll be able to have the s orbital blends with 2 of the p orbitals up here, and that gives us 3 equivalent blended orbitals or hybrid orbitals and 1 untouched p orbital. Okay, now these hybrid orbitals right here, the ones with s character, are the ones that are going to form sigma bonds. Okay, so if we have these equivalent orbitals form sigma bonds, that means we can form 3 sigma bonds, and they are going to spread out as much as they can. Those 3 sigma bonds are going to spread out to about 120 degrees, that trigonal planar configuration. Now, that leaves that untouched p available to form pi bonds, because that untouched p is going to go above and below the plane of that triangle and allow it to bond above and below any sigma bonds you have available to it. Okay, so what would that look like? Okay, so if we did that right here, these blue orbitals right here are representing those sp2 hybridized orbitals, and we have a total of 3 of them. So in this case here, we have one of the orbitals bonding to, actually let me change the color so it can be a little bit. One of the orbitals is bonding to a hydrogen here. One of the orbitals is bonding to a hydrogen here, and one of the other orbitals is bonding to an adjacent carbon here. Okay, so when we have this direct overlap of an s orbital with a hybridized orbital or two hybridized orbitals, we generate a sigma bond, or a single bond directly in between those two atoms. Okay, so that takes care of the hybridized orbitals, but that means that there is a p orbital untouched above and below that plane. Okay. So we still need a total of 8 electrons around each of those carbons. So what we're going to do is we're actually going to share above and below the plane of that sigma orbital, those p orbitals. 1 electron from each of those p orbitals to make another bond. And we call that a pi bond, and that we call that an overlap bond because it's up and over the sigma bond. And so what we'll see here is that's how we get to this second bond in ethylene. The first bond is a sigma bond made by orbital overlap, and the second bond is above and below that sigma bond because those two p's are going to overlap together. Okay. Now, that being said, we have 3 equivalent orbitals here, meaning that that shape of the bond to hydrogen, and bond to carbon is going to be trigonal planar. So the molecule itself is going to be planar, trigonal planar, and we're going to see that it has about 120-degree bond angles on it, just like we see in those trigonal planar 3 electron areas, 3 electron geometry zones. Okay, so we've taken all 3 p's and turned it into 4 equivalent electronic zones. We've taken 2 of the p's and made 3 equivalent zones, plus leaving the 1 p untouched. What if we did that one more type of hybridization and only blended 1 s and 1 p together, leaving 2 p's completely untouched? Okay, so if we did this, that means we would have a total of 2 electronic zones that would form sigma bonds, okay? Meaning these 2 electrons down here are going to form linear sigma bonds between 2 atoms. And we have a total of 2 possible pi bonds at above and below or outside of that direct bond between those 2 atoms to make 2 pi bonds. Okay. So what would that look like? Well, when we come into that, our sigma orbitals right here are linear, right? Because we only have 2 electronic regions. So that's going to give us a linear material. So that means one of these is going to be bonded to the hydrogen, and one of these is going to be bonded to the carbon, and that creates this linear axis between those 3 atoms. Okay. So if we have a linear axis on our atoms, we have 2 other electronic zones that we want to put in there. So they're going to be at the x and y opposite that axis created by those 3 atoms. So they're going to be spread out as far apart as possible. So what that allows us to do is that when we line up a p orbital, an unhybridized p orbital on one side and an unhybridized p orbital on the other side, it can overlap, forming a sigma bond. And in this case, we're going to form one on this axis right here. So this is going to be, let's call that the x-axis. It's up and down. Okay. But the other p orbital is not going to be in that same axis. We have to have it on a separate axis. In this case, we're going to call that the y-axis. And it's going to be over here. And so it's going to make another pi bond outside of that linear sigma bond. So that's how we get to these molecules like these triple bonds between carbon. The center bond is an sp-sp hybridized overlap bond that creates the sigma bond. The second bond is created by the pi overlap in one axis. The third bond is created by a pi overlap in the next axis. Okay, so if we think about it there, that's how we get our linear shape, because we have a pi on one axis a pi in the other axis, and our linear sp hybridized sigma bond in the middle. Okay, questions on hybridization? Okay. This is the key to why our molecules have different shapes. This is also going to lend us an idea of what things are going to react, okay? Because the sigma bonds are inside these pi bonds, I bet when we start looking at the reactivity of these things, the pi bonds are going to react first before the sigma bonds can react. And so we're going to see the fact that they're outside of that initial sigma bond, those pi bonds are going to be more reactive and do chemistry before we do anything to the sigma bond. Okay. All right, so that being said, the summary here is the idea that if we did not hybridize our carbon atom, it would not give us a tetrahedral structure. It would give us some weird T-shaped structure, okay? So it can't be just overlapping in the P's, in these two P's here. It has to be something else. And when we see four things bonded to carbon, we see it in that tetrahedral structure. Four equivalent orbitals are making four equivalent sigma bonds with those orbitals. And we see that in something very simple like this, this methane. Okay, so in this regime, we have about 3/4 of those bonds are from the P's, and 1/4 of those bonds is from the S. Okay. And we have this 109 degrees that we expect for a tetrahedral structure. Excuse me. Okay, so if we've only blended 3 orbitals together, 1 S and 2 P's, that means we have about 1/3 S character and 2/3 P character. But because we now have 3 equivalent electronic domains, they're going to be 120 degrees apart. And we have a P, which is the dumbbell shape above and below that atom, above and below that plane made by the trigonal structure here, that can make that second bond, that pi bond, above and below that plane. And that's why they have these neat planar structures to make these double bonds. The last type of hybridization is where we only use 1 S and 1 P. And so in that case, we have about half P and about half S. But we still only have 2 electronic regimes, which means that they have to bond 180 degrees apart. And we have in one axis, 1 P that's untouched and can overlap with another P. And we have a second P that is in the other axis, the X and Y axis, that can overlap with a P on an adjacent atom to give us our second pi bond. Okay, so questions about hybridizations. This is why our molecules in organic chemistry have the shapes they do, okay? Everything will go through some kind of hybridization or some kind of hybridization change. There's a question in the group chat here is, does this only happen with S and P, or do we need to know? It actually does happen in other orbitals. However, we would have to go into organometallics and inorganic chemistry to look at those hybridizations. So for our organic chemistry, all we need to know is SP, SP2, and SP3 hybridization. Okay? And we need to know the shapes of those molecules based on whether we have SP, SP2, or SP3 hybridization as well. So I will actually say, oh, look, we've gone from a double bond to a single bond. What's the hybridization now? We went from an SP3 hybridized orbital to an SP, or an SP2 hybridized orbital to an SP3 hybridized orbital. When we go from 4 bonds down to 3 bonds and a pi bond, we've gone from an SP3 hybridized orbital to an SP2 hybridized orbital. So we'll see those transitions. As the shape of the molecule changes, the hybridization changes too. All right. Any other questions on this? Okay. Now, I've used this example with carbon, but it's not just carbon. It's all of the elements in that group two. It's nitrogen, oxygen, and that we see it in most. And so when we look at the shape of things with three things bonded to nitrogen, we see that it basically does the exact same thing. We have an sp3 hybridized nitrogen. We just have 2 electrons in one of those orbitals giving us that lone pair. But we have 3 other orbitals that are allowed to bond with other atoms, okay? So nitrogen also has sp3, sp2, and sp hybridization. And we can tell the difference because of the number of times something is bonded to a nitrogen. So if we have 3 sigma bonds, we know that, and a lone pair, we know it's sp3 hybridized. If we have a double bond between nitrogen and some other atom, we know that we have an sp2 hybridized orbital and a p orbital available to it. And when we go into our extremes, we have this carbon-nitrogen triple bond. We have it just as if it was acetylene, an sp hybridized orbital plus 2 p orbitals to available. The only difference is in each of these, the lone pair is in the hybridized orbital. The lone pair is always in the hybridized orbital in the nitrogen. Okay. So that means that by looking at the hybridization, we can also tell the shape of the molecule. Okay. So in an SP, we only have linear. That's the only thing we have available to us. So that makes sense. We have 2 regimes. We have 1 way to do it. In sp2 and sp3, we have different structures. In an sp2, if you have 3 atoms bonded to your system, you always have a trigonal planar molecular geometry. However, if you have a lone pair, you're going to have a bent geometry. But the angle between these 2 atoms is going to be close to 120 degrees. That's how you can tell the difference between an sp2 hybridized bent molecule and an sp3 hybridized bent molecule, because this is going to be closer to 109.5. So when we go to the sp3, we have 4 equivalent areas. If you have 4 things bonded to it, it takes on the tetrahedral geometric structure. If we have 3 things bonded to it and 1 lone pair, we get to that trigonal parameter, like nitrogen-containing compounds. And if we have 2 ligands and 2 atoms bonded to it and 2 lone pairs, we ended up with bent, which means oxygen is also sp3 hybridized in water. 2 of those orbitals are taken up by lone pairs. 2 of those are taken up by bonds to hydrogen. Okay, so that means carbon, nitrogen, and oxygen all undergo sp, sp2, and sp3 hybridizations. Actually, oxygen only goes under sp3 because it has the 2 lone pairs already. But they all are the hybridized orbitals to get their geometric shapes. Okay, so that's the last I want to talk about that. I have a last set of slides, and it's all about intermolecular forces. Okay, so intermolecular forces are the forces that attract molecules together, and we have a variety of different attractions that we have. Okay, and these intermolecular forces control boiling point, melting point, solubility. And so by looking at how strong some forces are and how weak some forces are, we get an idea of how they can mix, how they can boil, and how they can melt. Okay, so the first thing we need to think about is the polarity of a molecule. So a molecule that has all of its bonds that are either all the same, meaning that they all have the dipoles are all pointing in the same, in equal and opposite directions, we tend to have something that's non-polar. But remember when we talked about polar bonds, that if one atom is more electronegative than the other, it's going to pull electron density away from the less electronegative atom, leaving it slightly positive. And if we have an unsymmetrical form of these bonds, we will see polarity in the molecule. Okay? Polarity in a molecule gives rise to a certain type of bonding that we're looking at, which is what we call dipole-dipole. Okay, so if we look at a wide variety of molecules, we can see that if there's a difference in two atoms, and one of the atoms more electronegative than the other, we will have polarity. So simple things like, we know water is polar because it has an unsymmetrical structure. An unsymmetrically substituted methane, where we have just one electronegative atom and 3 hydrogens, will have a dipole. In the case of something like this, where we have an oxygen, notice this is sp2 hybridized carbon and oxygen. It has a pole toward the oxygen. Oxygen's more electronegative than carbon, so it's going to pull electron density here. So with each of these molecules, we can see that there is a place where there's uneven pull between the electrons in the bond. Anytime you have that uneven pull in electrons in the bond, you have polarity. Okay. So for example, in this, they're both pulling in this direction here. And this, of course, has a bent structure because it has a tetrahedral electronic structure. Now, once you get up to something like hydrocarbons, like long chains where it's just a bunch of non-polar bonds, we don't see polarity. The polarity goes away because all of the different things cancel out. And even if we had electronegative atoms attached to a carbon, if we had an even distribution of electronegative atoms around that carbon, they would net pull against each other and end up with no polarity at all. Okay, so where does that leave us? Okay, well, that leaves us in the idea that if we have a polar molecule, that means that there's going to be one side of the molecule that has a slightly more negative charge than the other side of the molecule. And we call those partial positive or partial negative charges. And so in the way we write that is that for partially negative charges, we'll do a delta minus, meaning it's not a full negative charge, it's not an ion. It just has some more electron density on that side of the molecule than the other. And the other side of the molecule has a more positive structure, and so we call that partially positive. Okay, so if one side of the molecule is partially negative and one side of the polymer is partially positive, it is a polar molecule and therefore can do bonding. Okay, so now that we have polarity of a molecule done, let's talk about the 5 specific intermolecular forces we have available to us in organic chemistry. First is ion-ion, and these are in decreasing strength. Ion-ion is the strongest one we have. Ion-dipole is second. Hydrogen bonding is third. Dipole-dipole interaction, so just the partially positive side of and partially negative side of 2 different molecules. And then we have the last one, which is the weakest, which is induced dipole, induced dipole. It's also called dispersion forces or London forces. And they are the weakest of the set, okay? So as you go from a fully charged species to a partially charged species to something that can hydrogen bond and to something that's nonpolar, completely nonpolar, that's why they decrease in strength as we go down the list. So let's talk about each of those independently. So ion-ion forces, those are common. We have those in organic chemistry, but it's basically you have a full charge and a full charge, and that attracts it the most. Okay? But when you have a polar solvent like water or ether, you can dissolve ions in that. And you do that because you have the ion is the full charge right here, and you have a collection of partially negative parts of molecules all the way around that ion to help dissolve it, to balance that positive charge. We call that ion dipole force. Now, the next one is hydrogen bonding. And hydrogen bonding works if you have a polar bond between hydrogen and another atom, and so that you have a partially positive hydrogen and a partially negative side to another atom. And through space, that partially positive hydrogen will be attracted to the partially negative side of another molecule nearby. The more hydrogens you have that can do this hydrogen bonding, the stronger the interaction is. So it's very, very strong in water because you have two hydrogens that can hydrogen bond, and you have very small molecules so they can interact quite intensely. Okay, so let's look at the effect of hydrogen bonding here. On all of these are just constitutional isotopes. Basically, they have exactly the same elements, but they're arranged in a slightly different way. In this first one right here, we have two alcohols, two OHs on either side. That hydrogen on oxygen is one of the stronger hydrogen bonding systems we have. And if we look at the boiling point of this, when we have two things that can hydrogen bond, it's very high, 235 degrees Celsius. Okay. If we take one of those hydrogen bonders away and just made it into a dipole interaction, and we kept one of the hydrogen bonders, we see that the boiling point drops about 90 degrees, 85 degrees, okay? So all we've done is taken away this side that can hydrogen bond, and we just gave it something that it could hydrogen bond to, but does not itself hydrogen bond, and we've dropped that boiling point significantly. Now, if we do that again with the other side and we remove the hydrogen bonding from this side, so that all we have is a dipole-dipole interaction associated with this, we drop it again, okay? Another, 65 degrees, or almost 150 degrees from having hydrogen bonding. So this has hydrogen bonding times 2, this has hydrogen bonding times 1, and this has 0 hydrogen bonding. And we see that dramatic effect on the boiling point of these materials as they do. Okay. All right, well, that leads us to the next one. So we have ion dipole, and hydrogen bonding. The next most strong force we have is what we call dipole-dipole forces. So basically, this partially negative side of the molecule is attracted to the partially positive side of the molecule, and positive side of the molecule. And so they are loosely attracted to each other, and more so than in a van der Waals, but not as strong as if it was hydrogen bond. Okay, and so when we start thinking about how these molecules are stacking together, we're going to have, a hydrogen here and a hydrogen here and an oxygen here, and then maybe an oxygen here. So they're going to be attracted to the electronegative side of the molecule to an electropositive side of the molecule, and they're just going to interact as many times as they can. You never just have that one molecule. You always have a group of molecules around there, and they're going to reorder themselves to try to get that greatest dipole-dipole interaction. Okay, so that leads us to our last and weakest one, which is induced dipole. And this happens mostly in atoms or in molecules that have either very little polarity in their bonds or no polarity in their bonds at all. So what happens is that when a molecule kind of comes to the other molecule here, it's like, well, we all have the exact same electron density, but I'm gonna move a little bit of my electron density to the other side of my molecule, so we're slightly attracted to each other, okay? So we're inducing a slight change in charge, and that slight change in charge allows us to, dissolve with each other and kind of get close to each other, but not really interact very strongly. However, this is very much a function of surface area. So if you have some long molecules that can do this where they can lay across each other in a longer fashion, there's a stronger interaction than if you had two ball-like atoms, because now you have a very small surface area in between those two that can be attracted. Therefore, induced dipole interactions are very sensitive to the structure of the molecule. The more linear or flat it is, the more likely it is to bond. The more spherical it is, the less likely it is to bond. There's a less of an effect on that. So even if you had molecules of the exact same molecular weight, they are going to be less attracted to each other by these forces. Okay. And so these different forces affect our boiling point, our melting point, and our solubility, because like dissolves like. So if you have things that have dipoles, they're going to dissolve in things that have dipoles. If you have things that have hydrogen bonds, you're going to dissolve in things that have hydrogen bonds. And if you have things that have only induced dipoles, they're probably only going to dissolve things that are nonpolar that only have those induced dipoles. Okay. And ions very rarely solubilize anything. All right, so we're right at 10:50, and I have like 4 slides left. So, so I think what we should do is go ahead and break now, and I'm going to move the homework due to Monday after class on Monday, Monday evening at midnight, so we can get all the way through this, okay? Are there any questions? Let me go move.
I have a quick question about the homework.
Yes.
I know you said this already, but I just want to confirm. So you know how you allowed 2 attempts on each question?
Yes.
We can use both of them before we turn them in, or is the second one just for practice, like after it's graded?
So you have 2 attempts to answer it before you submit.
Okay.
So let's say you go ahead and do your homework, and then you went back and read something, and oh, that one's wrong. I'm going to go change it. You have an opportunity to change it before submitting.
Okay, thank you so much.
Okay. All right. Thank you. We'll finish up this and do a little bit with resonance structures on Monday, and then we will move on with chapter 2.
I had a quick question.
Yes.
So I'm still confused on where we can download the slides on Top Hat, because I have it open right now and I don't see it.
Okay. When I open Top Hat, I see where I can click on the assigned module, and it says download PowerPoint at the top.
Yeah, I have that open. I have the module 1 assigned, like I have that open, but I see nowhere where it says download.
Maybe share screen.
Okay.
Try and share your screen and we can see what you're talking about.
Me or you?
Either, I guess.
Okay, I'm trying to get to.
If you could share your screen.
Yeah, I can share my screen, but I have. I was trying to get to my student view to make sure that I had that on there somewhere. So, okay, let me share my screen real quick. Stop sharing this screen and start sharing desktop to this one right here. Share. Okay, see, when I see this, I have this download PowerPoints and allowed students to download original slides.
Okay, mine doesn't look like that.
Okay. Okay, I was going, let me go to student view. I have a student view that I can use to see if it's there. Okay, does anybody see where they can download it? Okay. Okay, what I will do is I will go ahead and upload the slides to Canvas so you can download them from there. Okay?
Thank you.
All right, I'll go start uploading those to Canvas right now. And I'll upload them as PDF so they don't take up so much room. Okay?
I have a question for that student. Are you sure you're not logged into Slate? It's kind of like Top Hat, but it doesn't give you access to all those things.
No, I'm logged into Top Hat.
The Texas State Top Hat. Okay, because
Yeah.
I was just on Slate, and I can see how that might have been an issue for some people.
Okay, no, it's on Top Hat.
Okay. Okay, but we'll put it on campus then?
Yeah.
Canvas then?
Okay, thank you.
Yeah, I see. It looks like a few students are having that problem.
Okay, so I did allow it. But I just don't know why.
Yeah, I have access to it.
Okay.
I don't know what's going on.
Okay, I'm going to go ahead and stop.